Hello Cloud Growers and welcome to part 2 of the Database Fundamentals lesson. In this lesson I intend to build on the learnings of part 1 and I'll introduce an overview of what happens when you run a SQL query, how that query is interpreted and passed to various components of the system, and I'll also talk about how SQL databases are constructed and various ways in which to scale SQL systems. So stay tuned and have fun with this lesson. Before I talk about the performance of a SQL database system, it's useful to highlight what a SQL database commonly does. A good start would be to say that a relational database management system accepts, runs, and returns data from a SQL query, and it does so anywhere from 0 to infinity times per second. When I talk about query processing, what do I mean? Well, first, a SQL query is broken into logical blocks: keywords, expressions, operators, restrictions, and nested statement blocks. Then a sequence tree is built, which contains a logical, sequential list of tasks to be completed. A component called the query optimizer reads the sequence tree and reviews all the different ways the tables can be accessed and other query optimizations which can occur. And it selects the fastest or the most efficient query which uses the fewest resources, and it updates the query tree. The final optimized version of the query tree, is called the execution plan. The relational engine then executes this plan and passes requests for specific rows and tables to the storage engine. The storage engine then makes calls to the hardware to pull in sections of the raw DB files, either directly from disk or from memory or a fast cache. The data is then processed and combined and returned to the client by the relational database engine. As well as query processing, the database has to read data, write data, and cache data. And finally, it has to organize data for efficiency. So when I talk about a relational database system, I'm actually talking about a number of discrete components, and each has different demands on the various logical and hardware building blocks of the system. The storage engine, for example, may benefit from extra non-mechanical storage, such as SSDs, or masses of memory for caching, where the relational engine benefits primarily from massive CPU and memory increases. Managing the performance of a relational system isn't always about throwing resources at the problem, but equally sometimes it is. So how do relational database engines scale? Scaling in the relational database world has always posed a challenge. The server can perform complex linked queries. The various components of the server needs to access all components of the data at all times. You may run a query against one table while your colleague in finance is running a different SQL statement with a nested query involving complex multiple table joins, and the different SQL providers have introduced different strategies of dealing with this scaling problem. The first is horizontal scaling. You start off with a database server. It may have a single quad-core CPU and some memory. You reach capacity and suddenly decide to grow the server by throwing extra CPU or memory at the issue. But soon you're going to reach a hardware ceiling, and unless you initially buy an enterprise class server which can naturally cope with a large number of CPU sockets and memory, you're going to have issues. But by doing so, by buying an enterprise class hardware system initially, you waste capacity when you don't need it. If you have a DB server running in a cloud environment such as AWS, another option is to start small and grow as your load does. But even with cloud environments, there's a limit. Beyond 32 cores and a few hundred gigabytes of memory, you will struggle to find support in a mainstream cloud provider for larger single instance servers. You could build a DB cluster, starting with your primary instance, which functions as a DB master or a writer. And this instance allows writes or reads. At this point, you could add a reader or a slave instance, which could provide you with 2 times reads, but no increases to writes. And then you could add another slave and another slave. Your only real limitation is that at some stage, writes are going to be the limiting factor, and adding additional read slaves or read replicas is not going to resolve write performance issues. It's worth noting that different DB vendors handle this type of performance scaling differently. Some, like MySQL, provide a dedicated storage platform per server, meaning you experience increases in a linear fashion to read performance. Others, like AWS's Aurora service, provide a shared storage tier which helps reduce the cost for the replicas and assists with storage performance management as the nodes pool their performance demands across the shared storage. So what about a better way of performance scaling? And luckily there are some techniques to achieve this, and we'll look at this next. Let's consider the following database of staff and customers. And let's assume for a minute that it's for a global retail chain, and it has millions, if not hundreds of millions of rows. The performance of the DB server is becoming a problem, and we've been asked to look at sharding it. So what options do we have? Well, first we could do a simple database segmentation. We could have two database servers, DB1 and DB2, and it's worth mentioning that this could be hundreds or thousands of databases, depending on the data scale. We could then decide to home a particular table on a given database server. This has the advantage of being simple to administer, as it doesn't need explicit support from a database or data model perspective. But, and this is a big but, done without DB support, it means that cross-table queries are either impossible to carry out or carry a substantial performance penalty. Another option is true DB support row-level partitioning. And this is where we can define logic which homes row sets to certain servers. And in this example, we have homed even number rows to one server and odd number rows to another. And we reverse that logic for another table. Now this logic can be based on row numbers, ranges of values in those rows, or a hash of certain fields. The advantage is that we achieve a near linear performance growth with the number of database servers. As we grow in servers, we split the rows over more and more database servers, and we can scale the performance across those servers, assuming that the rows are accessed fairly evenly. The cons are that in line with the previous method, there is a performance penalty when you're looking to do cross-table queries. And there are methods to mitigate this, but it's beyond the scope of this course. It is, after all, a DynamoDB course and not a relational database course. Well, that's it, Cloud Gurus. Thanks for listening. This is the end of the database fundamentals lesson. I know it was a long one and I haven't gone into a lot of detail, but that's intentional. I just want to provide enough detail on relational databases so that you can understand the differences when I start talking about non-relational or NoSQL databases. There is a lot more to learn if you're interested. You could study SQL, advanced database relational modeling techniques, and some specific skills on DB vendors such as Oracle, Microsoft SQL, or some open source engines. The topics covered in this lesson should be enough to provide you with a basic knowledge of differences between relational and NoSQL engines. Now, if you do have any questions, feel free to reach out directly or via the Cloud Guru forums. Otherwise, please go ahead and complete this lesson and move on to the next.